Hello, everyone. Very warm welcome to my digital assignment to presentation. My name is Pandan Ghosh, and today I'll be talking about my assigned topic, implementing keys and addresses in Python. I will quickly move to my presentation slides. So yeah. So basically, generating keys and addresses is an important part of working with cryptocurrencies such as Bitcoin or Ethereum. And Python enables us with many such libraries. One of them, which we're going to extensively use for this presentation, that would be the PyBitcoins library. Along with that, we are going to talk about a very important algorithm called the elliptic curve cryptography, and more specifically about the ECDSA. So now we will talk about key and address generation using the Bitcoin library. I will quickly move to a presentation to a code editor where we can learn as well as show the output for the key and address generation concept in Python. Yeah. So as you can see, there's a code where we're importing Bitcoin, a library, and we are generating a random private key. So after this, we are decoding that private key, which is actually an important step in encryption and decryption process. Soon after, we are computing the public key of the same private key. Then we are finding the hash address of the uh, public key. And also we are going to find the WIF encoded private key, where WIF is basically a wallet import format where we are basically displaying Bitcoin private keys using the base 58 check encoding scheme. WIF format was standardized in order to show all Bitcoin wallets to import and export private keys. I will quickly run the code. Sorry. Yeah, I'll quickly run the code. Yeah. So yeah, as you can see, the generated private key is this value, which is of length 5112 bits. And the decoded private key is this. The public key generated is of 1040 bits. And the corresponding address is this. Now the WIF encoded private key is this value. So basically, now we will talk about the compressed private key. So the compressed private key is when a private key is exported as WIF compressed, it's actually 1 byte longer than the uncompressed private key because it has the added 01 suffix. As you can see, where we are adding an extra 01 suffix to the private key. So basically, the term compressed private key means private key from which the compressed public key should be derived. Moving on, we will see how to multiply the EC generator point G with the private key to get a public key point. So quickly moving back to our slides, we can show that, we can show that elliptic curve cryptography is a type of public key cryptography used for secure digital communications. ECC, otherwise abbreviated, is used over finite fields to provide security. And also, ECC is ideal for use in resource-constrained environments such as mobile devices and IoT. ECC is widely used to secure communication protocols, digital signatures, and key exchange. ECC has also been adopted by many organizations and is now a standard in many security protocols. So the elliptic, before that, we will talk about ECC in detail. So basically, ECC is a certain algorithm where if we multiply the EC generator point G or the generator point by a certain integer K, then let that be the private key for us, then we can obtain an EC point P, which is actually the corresponding public key. So as you can see in the code before, I'll go back to the code. Yeah, so you can see that there are two coordinates. The first one is the x coordinate and the second is the y coordinate. And here we can see the hexadecimal encoded public key and also the compressed version of it, because compressed keys are easier to process. And also you can see the compressed Bitcoin address using the B58 check. Moving on, we will go to the ECDSA. So ECDSA is actually the elliptic curve digital signature algorithm. So I'll quickly move to the code and then I'll explain. So basically, no, first I will go to the ECDSA steps and then we'll go to the code for easy reference. So basically, ECDSA is an elliptic curve signature algorithm is basically a popular public key cryptography algorithm used to ensure the authenticity, integrity, and non-repudiation of digital data. So it is based on the mathematical properties of elliptic curves and is considered to be more efficient alternative to the DSA algorithm or the RSA algorithm. The ECDSA algorithm is used to sign digital data and also to verify the authenticity of the data using private and public keys. So in this algorithm, a user generates a public key and private key using an elliptic curve. Now the public key is used by anyone who wants to send a particular message or perform a particular transaction, while the private key is kept secret. So as to as it is used to sign the messages. Now you can see that the elliptic curve can be used. 1 second. Yeah. So the elliptic curve. Yeah. So the elliptic curve can be used where we actually take a point and the signature is calculated. To compute the signature, we get the value of s. We have to compute k power -1 into the hash of the message digest plus the private key into r. So now r is the x coordinate. We have to compute r. We have to find the x coordinate of the point obtained by multiplying a new random integer k with the base point or the EC generated point, and to take the result modulo the curve order. The signature is the pair of values r, s. To verify the signature by computing the inverse of s modulo the curve order and multiplying that with the hash of the message digest and the inverse of r modulo the curve order. If the computed point is equal to the expected value, then the signature is valid, otherwise it's invalid. Now we move to the SECP 256K1 public key cryptography algorithm. So the SECP 256K1 algorithm, which we're going to explain using a code, uses the following elliptic curve equation where y squared equal to x cubed plus ax plus b. Now we'll define each parameter where p is basically the finite field where the elliptic curve is present. Now a and b are the parameters. A is 0 and b is 7. G is the point, is the base, the compressed base point, and we can also uncompress it, but it's not required right now. Also n or r, if we can define, is actually the order n of g and the cofactor, which is actually a value as shown in the screen. Moving on to the implementation of ECDSA in Python. I'll quickly clear the screen and explain. Yeah, so we can see in the code that we have defined P, R, or you can say it as N, A, B, and G, X, and G, Y. We have imported the necessary libraries, ECDSA, OS, BINS C11II, and ECDSA.util. Everything has been imported properly here. So now we will execute the code. First, as you can see, the steps are same. Initially, we have to first compute the random secret key. Then we have to get the points of the public key using the random secret key. And we have to uncompress that public key using the unhex lifi function of the BINASCII library. So let's execute the code and see the output. Yeah, so I'll execute the code. Okay, so let's zoom in and explain the output. Yeah, so basically the secret has been computed as this random value in decimal format so that we can understand the value. And the EC point generated using the same is this value. Also, the Bitcoin public key, which is of interest to us, is this value. So overall, we can say that ECDSA is a good library, but it has a certain security considerations. So the library is not designed entirely for security. It uses a quality wrapper. Like if you're processing sensitive data, we can use a quality wrapper like PYCA or cryptography, other methods. And the library is primarily used for interoperability testing and teaching. So, and also the library is not protected against against the side channel attacks. Now, how can we as users or programmers be secure while using this library? We should not allow attackers to measure the time it takes to generate a key pair or sign a message. We cannot allow the attackers to run a code on the same physical machine during the key pair generation or signing. We should not allow attackers to measure the power or the RF interference generated during key pair generation or signing. Loading the private key alone, note that, can trigger key pair generation. So all operations can become vulnerable to the attacks. Even one operation with a private key can enable a sophisticated attacker to fully reconstruct the private key. Thank you. That was my presentation for my digital assignment 2. I will be looking forward to my evaluation for the same. Thank you so much.